Hello and thank you for coming to my talk. My name is Brett Green and I'll be showing you the Landau level phases in bilayer graphene under pressure at charge neutrality. We are interested in Landau levels in bilayer graphene as a platform to build many body ordered states. The more single particle states we have as ingredients, the more many body states we can make with them. These states are labeled by spin, up and down, valley, plus and minus, approximately equivalent to layer, and orbital 0 and 1. This gives us 2 by 2 by 2 equals 8 low energy Landau levels. In experiments, we can control which Landau levels are filled, and hence which ordered state we get, by adjusting magnetic and electric fields. We can detect transitions by peaks in conductivity or capacitance or by troughs in resistivity. By plotting the locations of these transitions in the plane of magnetic and electric field, we can produce phase diagrams. However, these states are difficult to characterize experimentally, and this motivates us to study the ground state phase diagram theoretically. Theoretical study also helps to shed light on the physics behind the competing ground states, so we use a tight binding model with interactions in the Hartree-Fock approximation. At low magnetic field, spin and valley polarized states are present at any pressure. Recall that valley and layer are coupled, and we see that there is a general trend of layer unpolarized states, such as this blue spin polarized state, being replaced with layer polarized states, such as the valley polarized state, at high electric field or high bias. We also see that at elevated pressure, there is a partially layer polarized intermediate state shown in orange. It is also partially orbitally polarized it is also partially orbitally polarized, and as we increase pressure and magnetic field still further, other orbitally polarized states appear, ending with a fully orbitally polarized state shown in green. Let's explore this effect in a little more detail. The principal effect of pressure is to increase the growth of the orbital gap with magnetic field. As a result, at high pressure, orbitally polarized states require lower magnetic fields to be stabilized. The reasons for this is that interactions dominate at low magnetic field, but the orbital gap will outweigh it at high magnetic field due to linear scaling. The spin and valley polarized states are stabilized by the interactions, whereas the orbitally polarized states are stabilized by the non-interacting dynamics. Let's now compare these results to experiment. Experimental evidence suggests that all transitions are sharp and discontinuous, not broadened and continuous. Previous theory using similar models had found continuous transitions between the spin and valley polarized states. Our work has resolved this discrepancy by finding a sharp transition by including new details in our treatment of the interaction. More specifically, in 2013, Lambert and Cote used a two-band effective Hamiltonian, which produced a simplified wave function with a single harmonic oscillator state. They take this state to be spatially confined to its layer. In 2016, Notha and Joliker used the full four-band Hamiltonian, which produced a wave function with multiple harmonic oscillator states. They continued the approximation of treating this state as spatially confined to a single layer. We use the full four-band Hamiltonian, but we respect both the layer splitting of the wave function and the out-of-plane extent of the PZ orbitals. To make a comparison within the same model, we calculated hypothetical phase diagrams in which neither, then one, then both of these effects were included. They have two major changes that they make to the phase diagram. First, they bring in orbitally polarized states at lower magnetic field by weakening exchange, and secondly, they get rid of the coherent superposition states, or the continuous transitions. Between the first and the second plot here, we see that interactions are substantially weakened by the inclusion of the layer split four-band wave functions, and that at low magnetic fields, superposition states no longer appear. between the second and third plot when we also include the spatial extent of the pz orbitals. Interactions are weakened slightly further, and no superpositions appear at all. The reason that interactions are weakened is simply because of delocalization. Both the spatial extent of the pz orbitals and the layer splitting wave functions delocalize charge and hence weaken interactions. As for superpositions, these are driven by interactions, and so for a superposition to be favorable, it must weaken the direct interaction more than the exchange interaction. Once we account for the layer split wave functions and the spatially extended pz orbitals, this is no longer the case. Thank you for your attention. Please feel free to send me any questions if you are interested.